Remember, Sally, when I said the first query is always the hardest?
That's right, Major. You did.
I lied.
Welcome to this video on querying SQL Server. My name is Kevin Wiesel. I am the proprietor of Catalxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. In the prior video, I promised you a gentle walk through T-SQL syntax. In this video, let's get a little less gentle. We're going to build on the basic components of a select query and introduce joins. Last time around, we looked at data from one table in the Chicago parking ticket dataset, parking violations. This table has a lot of useful information in it, but we had to talk about things like violation ID 1 without really knowing what that ID represents. We are going to rectify this shortcoming and provide our users with some sweet knowledge. The way that we connect tables together in SQL is through the join operator. Typically, we talk about join as having a left-hand side table and a right-hand side table. So, for the sake of simplicity, I'll use similar terms and run the risk of a pedantic comment or two about how virtual tables are not tables and the like. The worst part about it is, I want to be the pedantic commenter. On the left-hand side, we may have a table like parking violations. On the right-hand side, let's suppose we have a lookup table with violation details. The intent of a join is to, for each item on the left-hand side, use one or more columns and match to an equivalent column or set of columns on the right-hand side. From there, we can think of the resulting output as one big table from which we can choose whatever columns we'd like. By the way, if you're curious about why we would even design things this way, there's a really good reason: database normalization. I've got a whole series lined up for that topic. Oh, believe me. That's the really simple explanation for a join, but I think it's easier to talk through this in code, so let's jump to the demo. Here's a query which is probably familiar to you if you saw the last video. We are getting details on 50 tickets for a particular violation ID and officer ID. This query is nice and all, but most people probably don't know what violation ID 1 means. Fortunately, there is a separate table, tickets.violation, which includes the information we need. In order to bring in data from that table, I'm going to use a join. Specifically, let's use an inner join. Inner join is a fancy way of saying that we expect every row on the left-hand side to match up with at least one row on the right-hand side. The database design pattern we're following here is that violation is a lookup table, which provides additional context to our main table. Also, a lookup table has exactly one row for 0 or more rows in the main table. In other words, we will have exactly one row in tickets.violation with a violation ID of 1, and we may have 0 or more rows in parking violations with a violation ID of 1. I need to do more than simply say we want an inner join. I also need to provide the join criteria. In this case, I want to join on violation ID. So I'll take the left-hand side's violation ID and match it to the right-hand side's violation ID. Running this query, I get back exactly the same results as the first time around. That's because I didn't include any of the new table's columns in my select clause. Let's add violation code and description to the select clause, and now we see them in our result set. Violation ID 1 means that parking or standing is prohibited anytime. If I remove the violation ID from the where clause but leave an officer 32024, things get a little spicier. See, officer 32024 doesn't just write tickets for malignant standing, but also people who park next to a fire hydrant, or even worse, a crosswalk. So that's an inner join. The next type of join I'll talk about is a left outer join. The idea of a left outer join is that we will get back one row for each relevant row on the left-hand side, regardless if there is a matching row on the right-hand side. Relevance here means that we take into account filters, other joins, and anything which might otherwise eliminate the row before we need to care about it. If we change our inner join to a left outer join, it doesn't really change anything as far as this result set goes. That's because of the nature of this lookup table. But let's do something dumb, just to see how we can find a difference. I'm going to add something to the join criteria, where the parking violation's ticket number is also equal to the violation ID. Mind you, this is dumb from the standpoint of writing a valid query. But when I run this, we can see that the violation code and description are now null. That's because there were no rows here in which both the ticket number and the violation ID matched, so we could not meet the join criteria. Remember that SQL Server doesn't have a semantic understanding of your join criteria. It does what you ask of it, nothing more. Therefore, give it dumb join criteria, it'll give you a dumb join back. If I switch this back from a left outer join to an inner join, we get no rows back. So left outer join gives us at least one row per row on the left-hand side, whereas inner join only gives us a row if there is a match on both sides. Some of you may currently be looking at your hands and thinking, I have a left hand and a right hand. I wonder if joins in SQL do too. Unlike Captain Hook, they do. A right outer join is just like a left outer join, just backwards. With a left outer join, we get at least one row per relevant row on the left-hand side. With a right outer join, we get at least one row per relevant row on the right-hand side. Let's switch this dumb query from an inner join to a right outer join, and we get back nothing. This is a scenario in which our where clause implicitly changes our query. You see, the where clause here specifies officer 32024. Our join specifies that we include all of the violation details, as well as any parking violations which match this criterion. Well, we already know from the inner join scenario that there are no matches for officer 32024, so based on the behavior we saw in a left outer join, we would expect things like ticket number and officer ID to be null because there is no left-hand row which satisfies our join. When we then apply the filter on officer ID, no rows satisfy the query and we get an empty result set. But wait, why do we apply the filter after the join? Well, remember this table from last time around? Yeah, join slots in between a from and a where. This means that the database engine processes the contents of the join before applying a where clause. So even though the base table parking violations has officer ID 32024 in it, the virtual table we created as a combination of parking violations, right outer joined with violation, does not have a record with officer ID 32024. Another way to put this is, because we have a column from the optional table in our where clause, we've implicitly turned this right outer join back into an inner join as we require results. Let's fix that by removing the where clause altogether. This query takes quite a bit longer because it has to join 54 million rows, but we eventually get our results back. We can see that all of the columns originating from parking violations are null, whereas the columns originating from violation have values in them. As a quick bit of advice, don't use right outer join. Every single right outer join in existence has an equivalent left outer join, and it's easier for people to think in terms of left versus right outer join. That's because left outer joins make sense reading and conceptualizing results top to bottom and left to right, whereas right outer joins require you to jump around. You have to think of violation and then jump back up to parking violations to conceptualize the result. As you add more tables and more joins to the mix, it becomes easy to mess something up along the way. In addition to inner, left outer, and right outer joins, there are two more types we will talk about today. The first is called a full outer join. A full outer join is the combination of a left outer join and a right outer join. In other words, we guarantee at least one row for each relevant row on the left-hand side, and at least one row for each relevant row on the right-hand side. Full outer joins are uncommon, though we sometimes see them in data warehousing and building up sparse matrices for reporting. The final type of join is the cross join or Cartesian product. A cross join gives you one row per combination of rows on the left-hand and right-hand sides. Unlike the other join types, cross join does not have any join criterion. So if we were to cross join parking violations and violation together, we'd get back approximately 54 million times 177 rows, or just under 10 billion rows. Cross join is a great way to build up lots of rows of dubious quality. Why does cross join even exist? Well, sometimes you need it for business purposes, but the main reason is that in relational algebra, all joins are Cartesian products, and then we subsequently apply filters. What this means is, technically, you can perform any other type of join as an equivalent cross join followed by the correct filters. But just because you can does not mean you should. We have to care about performance, something irrelevant to academians, especially once they get tenure. We want to give the optimizer and the database engine a fighting chance to return our query results in a reasonable time, and using the right kind of join can help us get there. Thanks for coming along with me for this ride, as we briefly covered 5 different varieties of join in SQL with examples in T-SQL. Let me know in the comments if you appreciated the fact that I avoided all of the awful join puns along the way. We'll have links and show notes in the description below, and until we see each other in the next video, take care.